Okay, we have two ideas today. The first idea is variability, and he's the easier one. And then the second idea is this idea of bias. He's the one that gets a little crazy. So we have some protesters here, and they're saying that whenever we are dealing with samples, we want samples that have low variability and low bias. So let's start with low variability. What we want when we take a bunch of samples is that those samples are close to each other, because the closer they are to each other, the closer we get to the real value. So if I look at this distribution, I don't want a distribution that's way spread out. I want a distribution that is tightly clustered around this true value of 12%. And what the portion of these notes for variability say is, as you take bigger samples, your spread starts to decrease and they start to center around the true value. So the key takeaway is you want to be taking large samples. So on this page, we have the spread or variability of the sampling distribution is determined by your sampling design and the size of the sample. So when we have design here, what they are referring to is you need to take a random sample. So design is referring to the fact that your sample needs to be random, and it'll either say random or it'll say SRS, which is the same as a simple random sample. Most of the samples we deal with are random. So design is usually always okay. The one that is not necessarily okay is sample size. So larger samples will give smaller spread. And the reason why is because I'll give you this example. So let's say that I want to know how you guys feel about distance learning Fridays. So I decide I'm just going to ask Vincent and Caleb. What do you guys think? Do you love them? Is it a thumbs up or a thumbs down? 2 thumbs down. Do I think that I should use their sample to represent the entire student body? Probably not. Probably not, because I could ask Vincent and Caleb and they could go totally 2 thumbs down. And then I could ask Hannah and Kinsey if she were here, and Hannah's so nice, she would never say anything negative, so she'd be like, yeah, it's okay. And Kinsey would be like, no. And so then I have 50%. So I go from a 0% to a 50%, and then I could ask another group, and what if they're both crazy and said, yes, we love it, 2 thumbs up. 2 kids is not going to give us enough information about our school to say how you guys really feel about distance learning. But what if I asked 30 kids? That's probably a much better idea. I could ask all of you, and most of you would probably say thumbs down. But if I asked a random sample, I wonder what I would get. So the takeaway is you want your samples to be random. Maybe you guys would tell me the truth and say thumbs down, all of you guys, because you trust me. But if I took a random sample, I might get something different because they wouldn't want to say to a teacher, no, I hate it. Do you see what I'm saying? So there's a difference between a random sample and me just choosing you guys. You always want the random sample. And 2, the more people in your sample, the better information you get, the closer to the truth you get. It's better for me to ask all of you rather than just 2 of you. And that's the idea behind larger samples give smaller spread. So instead of using a sample size of 10, we would try to use a sample size of 20 or 100 or 1,000. Is that making a little bit of sense? So more people, the better. The larger the sample size, it's always better. Then this little portion says, if the population is much larger than the sample, at least 10 times as large, the spread of the sampling distribution is approximately the same for any population size. So that's just saying if you're pulling from a large enough population, it's got to be at least 10 times as large as the sample. Your distribution from your, so let me be way more specific. The spread of this distribution will never change. If the spread of this distribution is 0.1, if your population is large enough, it'll always be 0.1. And we get into this in a lot more depth in the next lesson. So if that's like, what are you saying? What you really need to understand is the larger the sample, the better. And this 10 times as large business will become clearer in our next lesson. So we want random design, random samples. We want big samples, as big as we can get them. And then lastly, population size is not important. Only sample size is important. So it doesn't matter if you're looking at a population that's 100 or 1 million, it's the sample size that we need to be big, not the population size. Because the more information we get from the population, the closer we get to the truth. You're hanging in? Okay, down here, we're not going to talk about accuracy, but these two would be considered a bigger variability. So when we talk about variability, we want to envision that it's more spread out. And what we would rather have is this, where all the points are clustered together. So these are low variability, these are high variability. They call that precision. These ones have more precision, these ones are not precise. So then where does this being on target or being accurate come from? That comes from deciding if an estimate is biased. So variability, we basically are looking at sample size. Now we're moving on to, is our statistic, is the value that we get from the sample a good estimate? So a statistic is unbiased if the mean of its sampling distribution is equal to the true mean of the population. So we're looking to see if our sample mean is equal to the true mean. I'm going to give you some symbols now. True mean would be mu. The sampling mean is mu sub x bar. So what this is saying is you added up every value in the population and divided to find the average. What this is saying is you took all of your sample values, added them up, and found the average. These two things need to be equal. So let's start with a really easy example. Let's start with the most basic population we've looked at so far, and that is my made-up class of 4 students. In my made-up class, we had 4 scores. We found that I could take 6 samples of 2 kids. So I have 6 dots on my sampling distribution that represent the average score of the 2 students. So these two students had an average score of 65, and then 75, and then 80, and so on. What is our average sample value? So what that looks like is mu sub x, and we would add all of these values. So we would add 65, 70, 75, 75, 80, 85. And we would divide by our total number of samples, which is 6. So this is the average of the two kids, but this is the average of all of our samples. So we plug that in, 65, 70, 75, 75, 75. That's too many 75s. 80, 85, divide by 6. And I'm getting that our average sample was 75. So our mu sub x bar is 75. The average of these 6 values is 75. Are you hanging in? Are you sure? Okay. Well, our true value, our true average test score was 75. So now what we're seeing is that mu sub x bar equals the true value. The average of all of my samples equaled the true average test score, which means that this estimate is unbiased. This estimate is unbiased. And what that means is that my samples give me a very good estimate of the population parameter. You're hanging in? Okay, now let's look at it for the gymnastics kids. We're going to look at this for our gymnastics kids. So we luckily have true mu. The true mu on Can You Do 51 was 20 steps. We made a sampling distribution, and it looks like this. It looks like 2 groups. Yes, babe? Uh-oh. Okay, I'll look for it. So let's see if the average of these samples equals our true average. So what we need to do is add up these 10 values and then divide by 10. Do you see what I'm saying? Was that a yes? Are you doing it? Tara, will you double check that you turned it in? Because I only have 3 B's. Can you do 51s? Is 30 seconds enough? Thank you. You're fine. Keep it for now and then hand it in. So you can write this down if you want to. I thought it was weird I didn't have one from you. I should have asked when you came in today. Okay, about 20. $10, $3. Okay, so I showed my work here just to be really thorough because I wanted it to be clear what I was adding. I ended up getting 200 over 10, which is equal to the true value. Is that what you guys got? So we have, for this one, mu sub x bar is equal to 20, which is equal to true mu, which means unbiased. And you can write that however you want to. This is just like a little bit of a shortcut. So one of the most important elements or pieces of understanding that you need to have from this process is that this is the average sample value. This guy is the average sample value. So if I can fit that in, I'm going to write that on my note page. I don't know if I'm going to be able to fit it in. So average sample value. Okay. This is where we got to buckle up because now it's going to get a little crazy. So I'm telling you guys, well, in order to know if it's biased or not, we got to add up all these values and then divide and find the actual average. But then underneath here, I have a bunch of examples that are just showing you graphs. So what's the connection there? And that's the last part of this lesson, talking about what this connection is. Thank you, dear. So let's go to page 503. Okay, this is our more complicated example. This is after the made up 4 students in my class. We go to this where I say, well, in real life, there's like 28 kids in a class. And what would it look like if we had to take samples from that amount of kids? And we came up with this dot plot. This dot plot has 64 samples. So this dot plot is 64 samples. He dropped. Okay. Now, family. If we wanted to, could we add all 64 of these numbers and divide by 64? Sure. We could make it a little bit easier by plugging it into our calculator and using the one variable stats to do this. But do we really want to do that? Like for realsies? No, I don't even want to do that. I didn't want to do it when I was making the notes for this lesson. So there's a shortcut. The shortcut is where the graph comes in. If your graph is symmetric, and this guy is roughly symmetric, if we ignore that point right here at 98, this graph is roughly symmetric. And even without that curve, hopefully you can see it. I mean, this guy's a little high, but truly, this is, if we folded it in half right on the center, it would line up okay. Is that making a little bit of sense? What you know then, what we now know about this distribution is that the median equals the average. What we now know is that the middle of this distribution equals what we would get if we added up all 64 values and divided by 64. That's one of the really awesome things about symmetric distributions, that we can say this. And maybe I should be a little bit more careful to say that they're like, maybe not going to be exactly the same, but they're going to be real close. Which means that we can use this median that I highlighted as our value of mu. So we can say that the average of these samples is 75 just by looking at the center of the graph, because he's symmetric. You're hanging in? So I actually found this for us because I wanted to be able to show you for sure that the values are very close. The actual value is 74.9. So if you plugged all of these dots into your calculator and really calculated the average, it's 74.9. So is that very close? Yes. Okay, so now let's decide if this is an unbiased estimator. Well, down here, I don't know why I have a question mark there. I'm pretty sure that I added these all up and that the true mu is 78. So I added what all up? I need to be more specific. I added these 28 scores together and divided by 28. And I got that the average test score is 78. So we have an average sample size of 75. That is not equal to true mu. So this estimate is biased. This estimate is biased. If your average sample size does not equal the true value, you have a biased estimator. Okay, so let's revisit the portion of the notes that goes through this. We know if a sample is unbiased if the average sample size is equal to the true value. We can go through in our samples and add them all together and divide them by the number of samples if we really wanted to, but often we can use the shortcut of looking at the center of the graph and using that as our average. So the real way to do it is this way. This is the real way. The shortcut way of doing it is this way, but you must remember it's the center only if you have a symmetric distribution. Are you okay? Are you sure? Okay, let me show you then what happens when your distribution is not symmetric, and that is, can you do 51 again? This guy is not symmetric. In fact, I personally think that he's a little bit skewed to the left. So in my mind, our gymnastics kids look like that. Well, what is our median in this graph? Our median is 1, 2, 3, 4, 5. So our median value is right here. Our median is 21.5. Notice that does not equal our average sample value. Why? Because this distribution is skewed left. We cannot use the shortcut on this problem because distribution is skewed, which means these things will not equal. Okay, now, just to help you out a little bit, they're always going to give you a symmetric distribution. So be on the lookout. Okay, now let's go back and look at those graphs underneath our note sheet. They're not even giving us the values on these graphs. They're not giving us any numbers or any symbols. So I'll fill them in for you. They're saying for this graph that the true mu is right there. That's what they mean by population parameter. That's either true mu or true p. Because remember, we might not always have an average. And they're saying, do we think that the average of this distribution is going to equal this population parameter? Definitely no. No. We could try to estimate, like, if we were using the location in the graph to estimate, I would say that this is mu sub x bar or mu sub p hat, just by looking at that distribution. Those things do not line up. So this is definitely a biased estimator. If it were unbiased, it would look like this, the one right below it. These two things do not line up, so this one would be considered biased. Are you okay on that one? What, Maddie? Ask me. Yes. So I'm just eyeballing it. Maddie's saying, well, where'd you get that line from? I'm just eyeballing this distribution. He's a little bit skewed to the right. So I'm thinking that his average value or his middle value is somewhere over here. Even if it were a little bit closer to these outliers, your average value still wouldn't be where this population parameter is. Does that help a little bit? So I'm just roughly estimating where I think the median might be on this one. On this one, I would definitely use the median because this is roughly symmetric. So in my mind, I would say, well, I bet you the median's in this tall bar. And that would be my mu sub x bar or my mu sub p hat. So this guy is definitely unbiased. The population parameter is right where the average of your sample would be. Do you feel okay about that one? A little bit? Okay. Next one, this graph has very high variability, but he is roughly symmetric as well. So because he's roughly symmetric, we can use his center, which is probably this, to estimate mu sub whatever, x bar or p hat. So my curve that I drew is not awesome because the peak should be where my center is, but it's okay. And then this guy's a really good one. So center of this guy is here. And population parameter is all the way over here. So this one is definitely biased. You're hanging in? Yes, no? Maybe a little? I think that you'll feel a little better about this idea as you do a couple of problems. So if you're feeling a little bit like, that's probably normal. and I'll be here to answer any questions that you have as you're working. So before we move on from this, let's just revisit this idea of variability, because that's where we started. So variability is where our distribution is either spread out or clustered together. If we're looking at these graphs, these two have high variability. These two have low variability. How do you affect variability? You want a random sample, but most of the time you're looking for large sample sizes. The other thing we're interested in is bias. We want our average sample value to equal the true value. How do we eliminate bias? The only way to get rid of bias is by taking random samples. So where do I want to write this? Your sample must be random. And then I'm going to write a weird thing in the bubble I just drew. I'm writing it is or isn't. And here's why. There are going to be questions that try to trick you and say, if I increased my sample size, what would happen to variability and bias? And they're going to say something like, it would reduce bias. You cannot reduce bias. It is either biased or not. It's a yes or a no. You can't be a little bit biased. It's either equal or it's not equal. So if reducing bias is ever an option, that is not the right answer. You cannot reduce bias. It is not a level. It is a yes or a no. You're okay? And then lastly, before we do one practice problem, we can revisit our bullseyes. And now hopefully this is making a little bit of sense. This guy would be biased, but high variability. This guy, not biased or unbiased, but has high variability. This guy, he's the double whammy. He's not good on both. He is biased and he has high variability. And then this is the one that we want. We want low variability, no bias. Okay, let's see on our last page here, page 506. Let's see what questions related to variability and bias will look like. So we have histograms, a histogram of the interval in minutes between eruptions of the Old Faithful geyser for all 222 recorded eruptions. That's like water, exploding water, right? They want to know, or they give us the population median. So the population median is equal to 75. Remember, way back when we very first learned this, I mentioned the most common things we look at are X bar and P hat, but they may also want to know about range, IQR, median, all that stuff. So this is an actual example of where we're looking at the median of a population. Well, they use software to take 500 random samples of size 10. So they looked at 10 geysers and they found the median value of those 10 eruptions. They did that 500 times. So they looked at 10 eruptions, found the median, recorded it, and then did it another 499 times. And this is the distribution that you get. They say that the mean of this distribution is 73.5. The mean of our sample, this is a big, ginormous subscript, medians. Because unfortunately, we don't have a nice variable for median. Sad day. Our average sample value, or the mean of our sample medians, is 73.5. Is this an unbiased estimator of the population? What do you guys think? No. How do I know? Well, does this equal the population median? Did our average sample equal the population median? Nope. The population median they gave us is 75. Our average median was 73.5. So this is a biased estimator. It says justify your answer. I think that this is enough of a justification. I can erase that question mark and now say that is not equal to. Suppose we had taken samples of size 20 instead of size 10. Would the spread of the sampling distribution be larger, smaller, or about the same? We increase sample size. What happens to variability or spread? Decrease. So I'm going to write this answer nicely. The spread of the sampling distribution would decrease. And then I'm going to make a note to myself. When n increases, spread decreases. That is always true. When n increases, spread decreases. Would it decrease my bias? No, because bias is a yes or a no. It's either biased or it's not. Okay, I'm not going to ask you how you feel because I don't think you're going to know how you feel until you try a problem. So can you do 52, number 2? You have that problem to finish in class. We get out at 10:29. Yeah, I think you'll have enough time. And you have 5, 6, 7 to finish, or just, 5, 6, 7. Did we talk about this guy last time? Did we talk about number 2? Okay. So I just, before I have you start, you can get into your Canvas lesson because there's 2 quick questions. And while you're doing that, I just want to tell you one thing about that can you do. If I can find my can you do. Golly. Okay. This is number 2. I'm just going to make sure that you understand what this is telling you. There's an internet business that ships out their orders, and they keep track of the number of orders that they fill per day. They do this for several years, so they look at thousands of days probably. And what they wanted to, well, after they have their 1,000 days, they have this 5-number summary. So of the days that they looked at the number of orders filled, that is the summary statistics. The minimum orders filled was 20. The maximum was 80. The median was 46, and then it gives you your quartiles. What these samples are is they take a sample of 40 days. So N is 40 days. And they calculate the range of these samples. So they look at 40 days, they find the highest amount of orders filled and the lowest, and then subtract them. So this would represent that there were 2 samples where the range of orders filled was 53. So this problem is not asking you to find an average or a proportion. This problem is talking about the range of the 40 days. And remember, range is max minus min. So in 40 days, there was a difference of 53 orders filled between the lowest and the highest. Okay, I think the solutions are up in the last lesson. So that includes this problem and 5, 6, 7 if you need help, but I also will be up and walking around, happy to answer any questions that you have. You're okay? Maybe? Okay. I'm writing up what you guys are doing because we've had a lot of information. You need to do lesson 52, part 2 questions. And then you need to finish. Can you do 52? So that's what you're working on for the next 30 minutes.